We've been talking about tension and compression, tensile stress and compressive stress, and they act on a plane that's at right angles to the line of action, to the line of the force. Shear stress acts parallel to the line of force. So, for example, here is a fillet weld that's welding one steel bar to a steel plate, and it makes a triangular piece of metal. And as the plates try to pull apart, there is shear along that weld material parallel to the line of action that's pulling on them. That's a shear stress. It's like this, acting on a plane that's parallel to the direction of the force, like a pair of shears, a pair of scissors. Next week, when we talk about stress-strain diagrams, we'll look a little bit more at what brittle means and what ductile means. But for now, we can think about what we know about a brittle material, like dry spaghetti is brittle. Concrete without any steel rebar in it is brittle. Cast iron is brittle. Materials like that, when they break without warning, and the face where the material fractures is vertical. Well, you can see down here in these bottom bars. See that vertical face there? It's truly perpendicular to the line of force. Ductile material is something that's a little bit more stretchy. It gives you some warning before it comes apart, and steel is an example of a ductile material. Ductile materials fail in shear, and so they begin to neck down, and those plates of molecules begin to slide past each other, and when they do finally break, the face where they broke is at a 45-degree angle. So here are a couple of test specimens. On the left is a brittle material where the face is just crosswise of the force. Here on the right is a ductile material where the face is at about 45 degrees to the force. Here are another couple of test specimens. Here, because this test specimen is round, the 45-degree face looks like a cup and a cone because the 45-degree face goes all the way around. And then here on the right is a brittle material, pretty flat. So this lets you begin to think about what is happening when you look at something that broke. If you see something that broke and it has a flat face, you know that it broke in tension. It pulled apart. If you see something that has a 45-degree face, you know that it broke in shear. Isn't that cool? And shear cracks at 45-degree angles are commonly seen in earthquakes, because in earthquakes we have part of the ground going up and part of the ground going down in some kinds of quakes. And so you'll have this shearing action. What happens to the structure is a 45-degree crack. Shearing happens in flat plates where you have a column and then a flat concrete plate over the top, and those columns can punch through, and when they punch through at a 45-degree angle because they are shearing. Here's a test specimen so you can really see those 45-degree lines. Here's a drawing of a column punching through a concrete plate. So to prevent these columns from punching through in something like, let's say, a parking structure, there are two things an engineer can do. They can make the plate more thick around the column, as we see in this waffle plate at the top. Or they can add a capital to the column. A capital is like an extra wide plate Also think snowshoe. Remember when we talked about snowshoes? This spreads out the stress across a bigger area. So a capital will help prevent shear stress. If you get something like a polarizing filter or something where you can see the lines of stress in a beam, you will notice that the direction of those lines of stress tends to be at about 45 degrees off of horizontal. Here's a simply supported beam, a support at each end and a load in the middle. 45-degree directions of stress at each end. Here are a couple of test specimens that show those 45-degree lines of stress on here's a simply supported beam. So what does this mean for you or your engineer? If you have something like reinforced concrete, where you have steel reinforcing bar, steel rebar inside the concrete, you think about how can you locate that rebar so that it really reinforces the concrete at those places where there will be 45-degree lines of stress. And two ways to do that are, one, like the picture at the bottom, you can bend up the end of the rebar at a 45-degree angle, which happens to be, how can we say, at 90 degrees to where the lines of stress are. So look at the picture at the top. There are the lines of stress where the shear stress goes across. Here's the rebar. Or you can use something called stirrups, that is, make vertical loops of rebar, and because there's going to be shearing stress at each end, you could put the stirrups closer together at the ends over the supports, farther apart out in the middle. Now think about last term when we looked at shear and moment diagrams. When we had a simple beam with a support at each end, do you remember how when the free body diagram jumped up, the shear diagram jumped up? It just jumped up suddenly, straight up. Lot of shear right here at that starting end. Here is a diagram out of a structures book. Let's look at the simply supported beam here on the right end. So there's the beam, there's the free body diagram. Here's something. Question, thinking about this diagram underneath the beam, do you think that is a vertical shear diagram, or do you think that is a bending moment diagram? And if you think back to what you know about shear and moment diagrams, you remember, yes, at the beginning of the beam, the load diagram jumps up, so the shear diagram jumps up. Then the diagram goes over until it hits the load in the middle, then it jumps straight down. So this thing here is not a shear diagram. It must be a moment diagram. So more and more bending moment until we get to the middle of the beam where that load is sitting. That's where our maximum moment is. In a beam, these shear stresses go at 45-degree angles, and they act through the web of the beam. This is a standard S-beam, what we used to call an I-beam, rather than a wide flange. You can tell because the flanges are kind of angled. Same idea, though. And this might make you think of trusses, where in a truss, you can have a bar with the truss that's carrying some load, and you can have a triangular hole in here because part of this beam web is really not doing anything. It can be air. Kind of interesting. So that was in buildings or bridges, structures. You can also use shear stress if you work in manufacturing. For example, let's say you have some kind of punching machine that is designed to punch a hole in steel plate. One well-known brand is an iron worker, but there are other brands. And there's a set, a punch and a die. Punch is just a tiny bit smaller than the hole in the die, and the punch punches down through. And so you put your piece of steel on top of the die, and then you hit your foot switch, and a hydraulic cylinder makes the punch come down and punch through the steel. Now here's the question. Is your iron worker strong enough to punch through whatever thickness of steel you've got? Now hopefully the machine that you bought has tables with it so you can just look these up. But if you needed to, you could figure this out, because you know your good old stress equation. Stress is force over area. And the machine will tell you how many pounds of force that hydraulic cylinder does. Your punch is going to punch out a round piece of metal. That's called a slug. Here's the thing. Think of that circumference around the slug as a ribbon. You just took a ribbon and wrapped it around that circle. The question is, what is the area of that ribbon? If you unwrapped it, could you use the area of that ribbon as the area in your stress formula? Why, yes, you could. And here I drew in PowerPoint, here's that ribbon, the strip around the outside of the slug, unrolled. So let's say the slug is, let's say it's a 1/4 inch plate, and the slug is 3/4 of an inch in diameter. So the height of our piece of ribbon is 1/4 of an inch. The length of our piece of ribbon is the circumference of the circle, 2 pi r or pi d. So the length of our strip is 2.356, as it happens in this case. So the area of our piece of ribbon is that times that. There's the area of our piece of ribbon. So now you could look up in your tables, which we'll be seeing as we go along through the term, and you could find out what is the ultimate stress, what is the breaking stress of this piece of steel? How much stress does it take for this thing just to totally break? If you can have more stress than that coming down with your punch, so force over area, you know that yes, you will be able to punch a hole in that piece of steel. Cool, huh?